Hello friends, welcome to another video in Digital Electronics playlist. We'll talk about hazards in digital logic circuits today. To understand hazards, we need to understand a key term known as glitch. A glitch is an unexpected output. It could be a momentary output, it could be just a spike or a trigger of an output which is unexpected. For example, if we are expecting a 1 at the output and for a moment we get a 0, that is known as a glitch. And then we could proceed on to form the definition of a hazard. Hazard is the potential of producing a glitch. In any logic circuit, the potential of getting a glitch is known as a hazard. We would say that the circuit is hazardous. The potential of getting an unexpected output for some condition of input is precisely known as hazard. The main cause of glitch or a hazard is the propagation delay of gates, and there is a specific combination of inputs for which we might get a glitch at the output. We'll discuss that in super detail. So we simply need to understand that the cause of glitch or a hazard is the propagation delay of gates, and we'll understand that with lots of examples in this video. And we know the propagation delay of gates is of the order of nanoseconds, from some 10 nanoseconds to 50 nanoseconds depending upon whether they are TTL based or CMOS based. Then we need to figure out the types of hazards that we may encounter. Hazards are classified as static 1 hazard, static 0 hazard, and dynamic hazard. Let's understand what a static 1 hazard is in this video. And by the definition, a static 1 hazard is expecting a 1 at the output, but 0 occurs momentarily somewhere in between. A logic circuit is placed under a condition where ideally we should be getting a 1 at the output, but some change may trigger a 0 at the output, and that is known as static 1 hazard. And now you could easily guess what a static 0 hazard is. We are expecting a 0 at the output, but 1 occurs momentarily. And dynamic hazard is the output transition is expected, but transition occurs with glitches. Now we'll understand that with examples. So the big question is, when can such a condition occur? When can such a condition occur where we are expecting a 1 at the output, but 0 can occur momentarily in between because of the propagation delay of gate? And the main reason of static 1 hazard is this condition that is written over here. This is the condition when we get a Boolean expression like a plus a bar, which essentially is 1 always. So if we give a 1 here or a 0 here, it does not affect the output of the Boolean expression. But does it actually happen in reality when we realize this expression with logic gates? Let's see that. So when we give a 1 at the input, y is 1. When we give a 0 at the input, y is 1. No problem. The input A goes from 1 to 0. Let's look at this scenario when there is a transition from 1 to 0. When the input goes from 1 to 0, this 0 is obtained at this input of the gate immediately, but a 1 is not obtained at the other input immediately. It will be obtained after certain propagation delay. So there is certain delay here. And during that time, both the inputs are 0. For that moment of time, the output will be 0. However, this combination of circuit should always produce 1. But for some time, when there is a transition from 1 to 0, we'll get a point where we will get a 0. Because during that time, both inputs of OR gates are zeros. But this is not true with the case of transition of 0 to 1, because when you change from 0 to 1, this 1 reaches at the first input immediately, and this 1 will eventually turn this thing to 0 after some time, and the output will remain 1 forever without any glitch. So what is happening here is when A is 1, the output is 1. When A is 0, the output is 0. This is what is expected at the output. But in actuality, when A transitions from 1 to 0, a glitch occurs. A moment of time occurs when the output becomes 0. And this is known as static 1 hazard. Any circuit which produces such a condition is known as a hazardous circuit with static 1 error or static 1 hazard. Now let's look at this K-map. If you have a K-map like this, you could reduce this K-map to this expression y is equal to a bar c plus ab. We get a logic circuit like this, and in this logic circuit, for a certain condition, please understand that the hazard does not occur for all the conditions. For a certain situation where B is 1 and C is 1, when B, C are 1, then the circuit should always produce a 1 at the output. You could see that when we put B as 1 and C as 1, the circuit will reduce to A plus A bar, which should always be 1. But during the time when B and C are 1, if A changes from 1 to 0, we'll encounter the same problem. The circuit should always remain 1, but it will produce a glitch when it changes from 1 to 0. And that happens because of the propagation delay of this NOT gate. Output should remain 1 even if A is 0 or 1, but when A changes from 1 to 0, static 1 hazard glitch will occur. Let's look at this case. If you reduce this K-map to some expression of Y output, we get A, C bar, D bar for these two and BC for these two. And you could easily figure out that we have a C bar here and C here. So if I put a condition of inputs where A and B are 1 and D is kept to be 0, we'll get to a condition where the output will become C plus C bar. And when we have an output like this, it should always be 1, but when C changes from 1 to 0, we'll get a glitch. So how do you find and correct this glitch? Now, correcting a glitch in digital circuit design terminology is known as covering the glitch. And you could easily find that through K-map if there are adjacent ones that are not being covered with single product term, then there will be a glitch and the circuit is hazardous. So we have these two ones which are adjacent, but they are not covered under the same product term. This one is covered by this and this one is covered by this. So when such a situation occurs, a glitch will occur and the circuit will be hazardous. And in this circuit, this one and this one is adjacent, but they are not covered with a single product term. So a circuit hazard will occur. So how do you correct that? We need to include these ones and these two ones in one single product term. And when you make a product term out of these two ones, this will be a redundant term. So that will increase the cost of the circuitry for sure. But when you include this BC in your circuit, you know that under this condition, now when B and C was 1, this will be 1. And when this is 1, no matter what the changes occur here and here, the circuit will always remain 1 at the output. So the glitch will be removed. So there is a trade-off between making a hazard-free circuit and a minimized circuit. A minimized circuit does not have redundant terms. However, in order to remove glitches, we might need to include redundant terms. So that was it for static 1 hazard, where a 1 was expected at the output but a glitch occurs. And I hope this tutorial was of help. If you liked the video, give it a thumbs up. I'll come up with static zero hazard in the next video. Till then, take care. Bye bye.